Fundamental primitives, points, lines, and polygons. Fundamental primitives in geometry are basic elements used to construct more complex shapes and structures. The three fundamental primitives are points, lines, and polygons. Points are the most basic geometric objects and have no size, shape, or dimension. They are represented by a single location in space are often denoted by a capital letter. In geometry, points are used as building blocks to define other geometric objects. Lines. A line is a straight path that extends infinitely in both directions. It is defined by at least 2 points and can be thought of a series of points that are connected without any breaks. Lines can be horizontal, vertical, or diagonal, and they have no width or thickness. In geometry, lines are used to create shapes, angles, and other geometric constructions. Polygons. A polygon is a closed geometric shape formed by connecting straight line segments. It is made up of 3 or more points called vertices, where each vertex is connected by a line segment to form the boundary of the shape. Polygons can have different numbers of sides and angles, and common examples include triangles, quadrilaterals, like squares and rectangles, pentagons, hexagons, and so on. Polygons are fundamental in geometry and are used extensively to study properties of shapes, areas, and volumes. These fundamental primitives serves as the building blocks for geometric constructions and form the basis of understanding more complex geometric concepts and structures. Objects with meshes. Objects with meshes are prevalent in various fields, including computer graphics, 3D modeling, and simulation. A mesh is a collection of vertices, edges, and faces that define the shape and structure of a 3D object. Here are some examples of objects with meshes. 3D models. In computer graphics and 3D modeling, virtually any object can be represented using a mesh. This includes characters, vehicles, buildings, furniture, and natural landscapes. Each object is typically composed of a mesh made up of interconnected polygons, such as triangles, quadrilaterals, that approximate the surface of the object. Terrain. Meshes are commonly used to represent terrain in virtual environments and simulations. The terrain mesh defines the elevation and shape of the landscape, allowing for the creation of realistic outdoor scenes, such as mountains, valleys, and hills. Architectural structures. Meshes are used to model architectural structures such as buildings, bridges, and monuments. By constructing a mesh that accurately represents the shape and layout of the structure, architects and engineers can visualize designs, analyze structural integrity, and simulate construction processes. Medical imaging. In medical imaging and visualization, meshes are employed to represent anatomical structures derived from imaging modalities such as MRI, CT scans, and ultrasounds. These meshes can be used for surgical planning and anatomical simulations and educational purposes. Overview. FEA is a numerical technique used to analyze the behavior complex structures under various conditions. Objects with meshes are used to discretize the geometry of the structure into smaller elements, allowing engineers to simulate and evaluate factors such as stress distribution, deformation, and heat transfer. Fluid dynamics. Meshes are used in computational fluid dynamics simulations to represent the geometry of fluid domains and boundaries. By discretizing the fluid domain into small elements, researchers can numerically solve the governing equations of fluid flow to analyze phenomena such as aerodynamics, hydrodynamics, and heat transfer. In summary, object meshes are prevalent in various domains, serving as the foundation for visual representations, simulations, and analysis, and virtual environments. They enable the accurate modeling and analysis of complex geometric shapes and structures in both virtual and real-world applications. Parametric surfaces. Parametric surfaces are surfaces in three-dimensional space that are defined using parameters. These parameters represent variables that determine the position of points on the surface. Parametric surfaces are often represented by vector-valued functions, where each point on the surface is described by a set of parameter values. Here's a general form for a parametric surface in vector form, where R is the position vector of a point on the surface. U and V are parameters that determine the position of the point. X, Y, and Z, U, V are scalar functions that define the coordinates of the point in terms of the parameters U and V. Parametric surfaces can take various forms depending on the choice of parameterization. Some common examples include plane. A plane can be parameterized using two parameters U and V, where each point on the plane is described by a linear combination of two vectors. Sphere. A sphere can be parameterized using spherical coordinates, where represents the azimuthal angle and represents the polar angle. Cylinder. A cylinder can be parameterized using cylindrical coordinates, where r represents the distance from the central axis, represents the azimuthal angle, and z represents the height. Torus. A torus, a donut shape, can be parameterized using toroidal coordinates, where it represents angles that determine the position of a point on the surface. Parametric surfaces are widely used in computer graphics, computer-aided design, and mathematical modeling because they provide a flexible way to represent complex shapes and surfaces. They allow for efficient computation and manipulation of geometric objects in three-dimensional space.